guys, today we're going to talk about permutations and combinations. So just to kind of review of the fundamental counting principle, we've already looked at this before, but it can be used to determine the number of possible outcomes when there are two or more characteristics. So it states that if an event of m possibility outcomes and another independent event has n possibility outcomes, then there are m times n possible outcomes for the two events together. So you can multiply the different number of events that occur in order to find the total combination and the total outcome of those events happening. So for a college interviewer, Robert has to choose what to wear from the following. He has 4 slacks, 3 shirts, 2 shoes, 5 ties. How many possible outcomes? So I've shown you this before where we can make a tree diagram, but the easier way to do this is just you can multiply. 4 slacks is independent from the shirts, which is independent from the shoes, which is independent from the ties. And all you're doing is just multiplying those totals together to find how many total number of outcomes you have. So that's going to be 120 outfits. Okay, so that's just a quick review. This kind of leads us into something called factorials. So a factorial of a non-negative integer, n, is denoted by n explanation points. So if you see this, which will come up on the SAT, it's the product of all positive integers less than or equal to n. So we take n, which in this case is going to be 5, and then you multiply by n. Let's write that a little better. You multiply by n minus 1, which is 4, multiply by n minus 2, which is 3, and you keep going all the way until you have 1 left over. So we're multiplying 5 times 4 times 3 times 2 times 1, which is 120. So 5 factorial in this case was the same as the other outcomes, but what a factorial does is you just multiply each number until you get down all the way to 1. So a permutation is an arrangement of items in a particular order. Order matters for a permutation, so it's going to be kind of confusing to talk about a permutation versus a combination. They're very similar, but a permutation, the order matters. So think about if we have first, second, third place. If we're trying to find people for office and we want specific people in as a president, vice president, treasurer, etc. Order matters, that's a permutation. So the formula that you have is the number of permutations n are chosen at r at a time. You can use this formula. So n permutation of r. So I usually say like n, like if there's 10 combinations with 3 seats, there's 10 permutations of r. That is equal to n factorial over n minus r factorial, where r is going to be between 0 and n. Okay, so n is always going to be bigger than r. So in this case, 5 permutation 3 is 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial, which is 5 times 4 times 3 times 2 times 1 over 2 times 1. There is a calculator function, and I'll show you guys that in class. There actually is, like, if you look at a TI-30, you can go to the probability function on the calculator, and it's like the number 1 and number 2 choice for permutation and combinations. But here, 2 over 2 is 1, 1 over 1 is 1, so we're just left with 5 times 4 times 3, which is 60 total outcomes. So let's look at an example of that. Combination lock will open when the right choice of 3 numbers from 1 to 30 exclusively is selected. How many different lock combinations are possible, assuming no number is repeated? So it matters here that there are 3 distinct numbers. So 3 numbers, and the order matters for a lock combination, because if the order didn't matter, then you could have, like, let's say the lock combination is like 1, 2, 3. If order didn't matter, it could be 1, 2, 3, 2, 1, 3, 3, 1, 2, etc. So you could have a bunch of different combinations. So this is a permutation because order matters. Also, it's really important here that we want to say assuming no numbers are repeated, because your permutation is going to change if you have multiple numbers that can be repeated multiple times. So that's going to be 30 numbers, permutation 3. So we want to choose 3 combination, a distinct 3 from those 30 numbers. That's going to be equal to Again, 30 factorial over 30 minus 3 factorial. That is 30 factorial over 27 factorial. And I'm not going to list all of these out because I think you'll be able to kind of figure out which three numbers I have to multiply together. So on, divided by 27, 26, 25, and so on. So you can kind of see these numbers here are going to go and cancel out. So really the only numbers that you're multiplying together to find the answer is 30 times 29 times 28. So 30 times 29 times 28 is 24,360. So there are 24,360 lot combinations. Okay, here's another example for a permutation. From a club of 24 members, a president, vice president, secretary, treasurer, and historian are to be elected. In how many ways can the officials or offices be filled? So this is a permutation because there's specific roles for people. So when you have specific roles for people, that means order matters. So we have how many roles? 1, 2, 3, 4, 5. And we have 24 people to choose from. So 24 permutation 5, that's going to be 20 factorial over 24 minus 5 factorial, which is 24 factorial over 19. That's 24 times 23 times 22 times 21 times 20 times 19 dot dot dot. 19 times 18 dot dot dot. So we're multiplying. We can cancel out the 19 and we can cancel out the 18. So the number of combinations is going to be found by multiplying the 24 times the 23 times the 22 times the 21 times the 20. So just using a calculator again, there is a specific function that you can use for a permutation, but if we're just setting it up using the formula, you'll find the answer that way as well. So this is crazy. 24 members, 5,100,480 different ways to arrange those members. So just think about if you had a club of 100 members and 5 roles. It's going to be like so many large combinations of how many people you can have. So this shows us now, so permutations. Now combinations is an arrangement of items in which the order does not matter. So it doesn't matter if someone is elected president, vice president, now order doesn't matter. I'm just choosing how many people that I need from a total. So the notation that we use is N choose R. So if I have 20 members and I want to choose 2 members, it'd be 20 choose R, 20 choose 2. Remember, N is always bigger than R. So since the order doesn't matter in a combination, there are fewer combinations than permutations. So order matters, you have a lot of permutations. When order doesn't matter, you don't have as many combinations. So here's our formula for a combination. N choose R. We're multiplying N factorial divided by R factorial, N minus R factorial. Again, it has to be between 0 and N. So if we're looking at 5 choose 3, that's 5 factorial over 3 factorial. N, which is 5, so 5 minus 3 factorial. So that's 5 factorial over 3 factorial times 2 factorial. And I'm just going to write this out as 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, 2 times 1. So you're noticing you're dividing by a much larger denominator, and that's going to make those number of terms go down. So 3, 2, and 1 can cancel out, but not the 2 and the 1 down below. So we have 5 times 4 over 2 times 1, which is 20 over 2, which is 10 different combinations. So let's look at a couple examples of that. To play a particular card game, each player is dealt 52 cards from a standard deck of 52. How many different hands are possible? So we have 52 total cards, and we want a combination of 5 different cards. So that's going to be 52, choose 5. Again, there is a calculator function using probability. Setting that up, that's going to be 52 factorial over 5 factorial, 52 minus 5 factorial. So that's 52, 51, 50, 49, 48, 47, and so on. We have 5 factorial, and then 52 minus 5 is going to be 47, 46, 45, and so on. So you'll see that you can cancel out from the 47 on. Come on there. There we go. So these are going to cancel out. So then you're left with 52 times 51 times 50 times 49 times 48 over 5 times 4 times 3 times 2 times 1. And I'm going to just use a calculator to do this to simplify those values. So 52 times 51 times 50. It's going to get very big very fast. So that's going to be 311 million. And then divided by 5, 4, 3, 2, 1. So that's 20 times 3 is 60 times 2 is 120. So divided by 120 is 2,598,960 combinations. So permutation is going to give us a lot more different combinations than if we're just looking at a combination. Student must answer 3 out of 5 essay questions. So how many different ways can they select it? So think about when you're signing up for college and they give you 4 different examples and they say choose to answer 2 of the essay questions. So think about how many different ways that students can answer those 2 essay questions. So we have 5 total outcomes, or 5 total possibilities, and we're choosing 3 of those possibilities. So 5 factorial, 3 factorial, 5 minus 3 factorial. That's going to be 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, 2 times 1. Okay. Again, we can cancel out the 3, the 2, and the 1. We're left with 5 times 4, which is 20, over 2 times 1, which is 10. So 10 different combinations. Okay, and then a last one example. Basketball team consists of 2 centers, 5 forwards, and 4 guards. And how many different ways can the coach select a starting lineup from each of the 1 center, 2 forwards, and 2 guards? So this is kind of an interesting one because it's like a probability. It's like an and independent. So each of these roles on the basketball team is independent. So centers are independent, 5 forwards are independent, and 4 guards are independent. So each of these represents a different combination of an outcome. So for the centers, there's 2 different possibilities for a center, but the coach is selecting a starting lineup of 1. The order doesn't matter here. We're not filling up specific. It doesn't matter what player is in which spot, but we're going to have 2, choose 1. And that's going to be the centers. We have 5 forwards, so we're going to have 5, choose 2. And the other independent event is the 4 guards. We have 4, choose 2. So you're multiplying all those values together to find the total outcomes for those positions. So 2, choose 1, it's 2 factorial over, that's going to be 1 factorial, 2 times 1 factorial, which ends up just being 2. Okay, this is going to be 5 factorial over 2 factorial, 5 minus 2 factorial. So that's just going to end up being 5 factorial divided by 2, which I believe is 10. I'm doing these rather quickly too, so check my math on a calculator. And then 4 factorial over 2 factorial, 4 minus 2. And I'm just using that calculator, that formula every time that I present it to you. So I'm going to check this one. 4 times 3 times 2 times 1 over 2 times 1, 2 times 1. That's going to be, those 2's and the 1's cancel out. So it's going to be 12 over 2, which is 6. So the total number of combinations is 120. And I got that by multiplying 2 times 10 times 6. So if we have combinations of different positions where each one is independent. So I know that kind of seems weird. Like it kind of seems like it could be a permutation. But I'm not trying to fill them all with people from the club, like the president, vice president one. I'm more so trying to fill each position as a separate event. It's not like choosing a vice president and we can have 6 vice presidents. Like it's each independent event on its own, which makes it still a combination. And when you have multiple independent events happening, we're multiplying, and that bolded and is telling me, again, multiplying for independent events.